Oh, you need to request access? I thought I gave everyone access already. Wait. Um, Let me try and see. Oh, you all need to this is annoying. Okay, I thought I gave anyone access. Oh, because you're not using UTM anyone with the link. Okay. Mm, okay. Try to use the new link. So I've made it so that anyone can access. Can you try and see whether you can do it or not? All right. Okay, so okay, meaning I don't need to give you guys access because anyone can open it. Okay, write it down, please. Okay, I'll keep this slide open here. So let's take about 5 minutes to maybe write down the important parameters. You can just write the numbers, or you can write the symbol, for example T1 or CP. And then once everyone is done, then we can start um, solving the question. You can also use sticky notes or the the text box if you're having trouble writing it down like this. Is anyone having trouble? Aren't there anyone writing on the Jamboard? You don't need to solve it yet. We'll solve it together. I mean, so just write down the important parameters first. Like I think someone is trying to write 206 kPa. Just something like that. Okay. What else other than the pressure is important? Do you think the parameters that you think you will need to use in your calculations? Okay, so the velocity. So we'll try until 9:15, 9:50, yeah? Then we'll try to solve the question. So the diameter of the tube, which is 0.0, okay? Good job. You already converted from millimeter to meters, and your conversion is correct. Okay, someone somehow already found the Prandtl number, which is 0.686. Okay, temperature 1 and temperature 2. Yeah, I think this is pretty much it. Okay, so let's try and solve this. So the important parameters that you can find here is actually the temperature, first temperature of the air going in, then the inside, the diameter of the tube and the velocity of the air, and then the because of the heating medium of steam. So we assume that the surface wall temperature, because of the steam outside the tube, is the same temperature of 488.7 Kelvin. Okay, so what do you think they want? Okay, they want heat flux, correct, and they also want the heat transfer coefficient. So another thing that is important is the length divided by the diameter is more than 60. So when what happens, why is it important to know that the length divided by the diameter is more than 60? Can someone tell me? Unmute or maybe write in the Jamboard. Why is L over D more than 60 is has to be stated? Does anyone remember? Okay, actually, if you recall from the previous class, length over diameter that is more than 60 means a fully developed flow inside the tube. So, if it's less than that, usually is it has some entrance region effect. So, which is why the equations that you will use to calculate sometimes depend on the L over D. So whether it's more than 60 or fully developed flow or not. So what we want to find here is the heat transfer coefficient H and the heat transfer flux Q over A. Okay, so good job here. So okay, so what the things that are missing here are Okay, so the missing things that are not in the question is the viscosity, the bulk viscosity of air, the conductivity K, and the Prandtl number. So usually if it's in a test or exam, you will be provided with some tables or appendices, tables from the appendix where you can find all these parameters for different sorts of fluids. For example, air is a fluid, and another common one is water, so it will be used as fluid. So depending on the condition that is given in the question, for example, in this question, the condition is 477.6 Kelvin. So you can find in the table for air. You find in the table for air, and then you just see the temperature that is a few temperatures will be listed out. So you find the temperature that you need, and then you read off the table all these values, the viscosity, the conductivity, the thermal conductivity, and Prandtl number, and all the other things. Okay, so you will see something like this during the in the assignment later. So I will be providing some questions like this, but not everything is inside the question. So sometimes you will need to use the tables to find the parameters that you need. Um, so since air is considered air in is 477.6 Kelvin, and then air going out is 488.7. So we need to account for the viscosity of air at different temperatures. Okay, so let's try to solve this. Wait, why can't I? So I'll go to Jamboard. So can you see this? Can you see the Jamboard? Yeah, you can see the Jamboard either way, so you can open it. So let's try and solve this. So first, for me it's easiest to if you want to make as little mistakes as possible, to convert the units. So whether it's English units or SI units. So in this case, we use SI units. So the bulk viscosity of the air coming in is 2.60, okay, times 10 to the power of 5 Pascal second. So you convert this by uh, okay, by using the conversion factor. So you will get 2.6 times 10 to the power of -5 kilogram per meter second. Okay. Oh yeah, I just remember one of the students are not able to come in this early, so it's okay. I will be uploading this onto the e-learning later. So using the Avogadro's gas law, we can so PV over nRT. So we can calculate the density because we can calculate the density to be using the molecular weight of air. So we can usually, if it's in the exam, I believe this something like this should be given. So the molecular weight of air is 28.97, but this is pretty common. So again, convert this into from gram to kilogram, and then this is the for using the ideal gas law. So you can find, you can use you can get this conversions. So this is converting for 1 meter cube is equals to 1000 liter, because we want to cross this and this out. And then 208 kilopascal, the pressure just now, divided by the standard pressure, which is this one, 101 times 0.33. Okay, then 270.2 K divided by where did you get 477.6 K is the entry temperature of air. Okay, so 273.2 is all the standard, and 101.33 kilopascal are the standard temperature and pressure. Okay, so you can get 1.509 kilogram per meter cube. Okay, so this is the density. Okay, so you might think about, why do we need the density? So can anyone tell me why we are calculating the density? What do we need the density for? Yes, correct. We need the density for, someone answered privately. I don't know what is with the setting, but never mind. So we need to calculate the Reynolds number. So for Reynolds number, if you remember, the formula is dV rho divided by mu. So we have mu, the viscosity, and we have the velocity V, and we have the diameter D, but we don't have the density. So that's why we are calculating it. Okay, so now that we have the density, we can go ahead and calculate the Reynolds number. So anyone, before we calculate, can anyone tell me why we need to know the Reynolds number? Not quite, not for comparison, but because we need to know whether the flow is laminar or turbulent. So even though in the question here, I've written the title that is heating of air in turbulent flow. So you already know that it's turbulent. So usually in the test or exam, they will not tell you whether it's laminar or turbulent. So you need to calculate and the Reynolds number to find out whether it's laminar or turbulent. So that's what we are going to do now. So someone already converted from meter to millimeter to meter just now, but I'll just write it down again, so you guys can the other students can follow. So the velocity was also given in the question earlier, and then of course the density, we calculated it just now, 1.509 kilogram per meter cube. So divided, okay, so divided by the mu. So mu in this case is the mu at the entry pressure, which at entry temperature, which is 260 times 10 power of negative 5. Okay. Kilogram per meter second. Okay. So what is the unit for Reynolds number? Does anyone know? I think uh you should have covered this somewhere. No. I mean that one is 2100 is the threshold for laminar flow. But what is the unit of Reynolds number? Meaning, is it kilograms or meter or seconds or what? Does anyone know? Why is everyone so quiet? I'm not even sure you're here. I only see one person messaging me. Anyone knows what is the unit for Reynolds number?
No units, Doctor.
No units, correct. So it's a dimensionless number. Okay. So good job. So even if you see here, if you cross everything out. Wait. 1 meter, 1, 2, 3, then meters cube, and then kilogram and kilogram. So you will get you will cross out all the dimensions. So in this case, you will get 1.122 times 10 to the power of 4. Okay, so like you said just now, it's dimensionless. But this is also equal to, if you write it in full, 11220. So that 1, 2, 3, 4. Okay, so this is more than 6,000. So if you remember, if the Reynolds number is over 6,000, that means that the flow is turbulent. Okay. So because the flow is turbulent, we can use the formula to calculate the Nusselt number. For L over D, that is more than 60, and for turbulent flow. So this is the formula. So Nusselt number equals to HLD over K equals to 0.027, and RE, the Reynolds number, power of 0.8, and PR, the Prandtl number that we can get from the appendix. So 1 over 3. Mu bulk over mu water. Mu of wall, sorry, not water. Okay. So, what do you think we want to get from this equation? So we have, if you remember, we have this, the mu just now. We also have the mu wall, and we have the Prandtl number. We can get this from the appendix. And we just calculated the Reynolds number. So we have all this. So what else do we need? What does the question ask for? Think about what else is given in the question. So K
L over
is
D,
also
Doctor.
given. Sorry?
L over D, 60.
L over D 60, we already know that. But what do we want to calculate from this equation? We also have diameter. So what we want is actually this, HL. So HL is actually the heat transfer coefficient. And if you look back at the question just now, they did ask for the heat transfer coefficient. So that is what we want to calculate. Okay, but good try. So from this, we just substitute in all the values that we already know. So the diameter is 0.0254 meters. Okay, the thermal conductivity is also given earlier, 0.03894 watts per meter. Okay. And then just plug into the formula just now, the Reynolds number 1.122 times 10 to the power of 4. Then the formula says it has to be times to the power of 0.8. Then times the Prandtl number that you can find in the appendix. Okay. So the mu bulk is 2.6 times 10 to the power of negative 5. Okay, Pascal second divided by the wall viscosity, or the viscosity of the air at the wall, the surrounding air. So 2.64 times 10 to the power of negative 5 Pascal second time power of 0.14. So the values for viscosity can also be retrieved from the appendix. which I will share with you in the assignment. So if you shift this over here, over onto this side, and this one also onto this side, you can solve for HL. So if you take out your calculator and solve this, you will get 3.2. And then as for the units, okay, this is meter squared. So wait, so for the units, we can the unit for HL is equal to watt per meter dot K. Okay. Watt per meter squared dot K. Okay, so from here, now that we have HL, so we have already solved one of the things that the question wanted. So this is done. So the other thing that they want is the heat flux, if we remember. So heat flux is rate of heat transfer Q divided by the area. Okay, so is equals to HL, the heat flux, the heat transfer coefficient, minus delta T. So the delta T in this case is T wall minus the temperature of air going in. Okay, so we can HL, we have 63.2 watt per meter squared dot K. And then T wall will be 488.7. This is from the question. Minus 477.6 Kelvin. So in this case, we will get 701.1 meter squared over meters. Sorry, no. Wait, yeah. So because for in this case, because we are using the formula, so we have the formula already stated that using this we will get HL with these units. But for this one, we can actually just cross it out, the K here and the K here. So you will get a heat flux of 701.1 watt per meter squared. So this is settled. Okay, so question 1 is done. Okay, wait. Okay. All right, so let's move on to the second. Any questions about this first example? If not, we can move on.
Doctor,
Yes.
Doctor,
Yes.
from where we can find the Prandtl number, in which appendix, Doctor?
I can't remember because wait, let me see, because it depends on which book you're following. So the appendices might differ, but the appendix should be there will be a title in the appendix. So if it's for water, then you will read from the water table, and if it's for air, then it's for air. Then you can see clearly all in the different columns will have different parameters, for example CP or Prandtl number, so you can clearly see from there. So just make sure that you got the right fluid. If it's air, then it's take from the air table. Then if it's water, from water, and then you just see what are the parameters that you need, and the temperature that your question is given. Is that clear? All right. Okay. So let's move on to the second question. So I'll share again the slide just now. Okay, so wait, I can't see. Okay, so in this case, we have water that is heated by steam. So again, because this water is heated by steam, the steam will be in the surroundings, which means that convection heat transfer occurs in this case. So the question goes like this. Okay, so water is flowing in water is flowing in a steel pipe. So the diameter of the pipe is given as 1 inch. But in this case, when we are using steel pipe, we are considering the inside diameter and the outside diameter is slightly different than it's not actually 1 inch. The specifications is 1 inch, but it is the inside diameter and outside diameter is slightly different. So there is also an appendix for this, where you can find for steel pipe, you can find the for different inches here, you can find the inside and outside diameter. Okay, so the average temperature is 65.6, the average temperature of water, and the velocity is 2.24 meter per second. So again, it is being heated by the steam in the surroundings outside the pipe wall. So the water flows inside the pipe wall, and then steam is actually the hot steam is actually outside the pipe, and then because it's in contact with the pipe, it will heat up the water that is inside. So the outside heat transfer coefficient, HO, is already given in this case, 10,500 watt per meter squared K. Okay, so first they want you to calculate convective HI, then calculate overall coefficient UI, and calculate heat transfer Q. So we also have the length of the pipe. Okay, so I already basically given it out to you, but try to go to the Jamboard again and do what we did do what you did for question 1, and write down the important parameters that you will need. So let's take 5 minutes to do so until, okay, about 7 minutes. So I'll give you until 10:20 to write down the important parameters like you did in the first question. Okay, the temperature, that is the temperature of water, 65.6 degrees Celsius, correct. Then we have the velocity and HO, yep. We'll need all this later to calculate. What does the question need? What does the question ask for? There are 3 parts in this ABC. Okay, HI, yeah, we need that, correct. What else? We have the okay, UI, correct. Then there is one more parameter that is given just now. Other than the temperature, we need the, yes, heat transfer rate Q, correct. Then also the length, if you remember, is given in the third part of the question, 0.305 meters. Okay, good job, guys. That was quick. So let's see. Okay, so the important information is that the specifications of the steel pipe, because we need this information to find the diameter, outside and inside diameter from the table later. So we have the inlet temperature, the velocity, the steam temperature, or we can take it as a TW perhaps, and then the outside temperature, and then the outside heat transfer coefficient. So we need to find the convective coefficient, the overall coefficient, and then using the length, we need to find the heat transfer rate Q. Okay, so from the appendix, we can find that for 1 inch schedule 40 steel pipe, the inner diameter is 0.0266 meter, and then the outside diameter is 0.0334 meters. And then for the thermal conductivity, I think someone already found it, 45 watt per meter Kelvin. Okay, so we all, similarly to the first question, we also need to use the appendix to find the properties of water at 65.6 degrees Celsius, because this is the inlet water temperature. So you can find from the appendix the Prandtl number, the density of water, because if you recall from our very first lecture, the density of water is different at different temperatures. So this is why convection can happen in a water kettle, for example. So if it's heated from the bottom, the hot water will become lighter, as in smaller density, so it will rise to the top. So that's why we need to consider the density of water at different temperatures. So for the conductivity K 0.633 and the mu of 4.32 at times 10 to the power of -4. Okay. Yes, some already wrote it down, the diameter, that is. So because in this case, because if you read the one above here, it's trial and error solution. So the temperature of, while the temperature outside is given, the outlet temperature of water is not given. So because if logically, if you think about it, even though the steam is 107.8 degrees, not all all the heat from the steam will transfer into the water. So why is this? Why isn't water heated until 107.8? Does anyone have any idea why? Why isn't all the heat transferred in the sense of change in temperature? It's actually because if you remember, there are resistances which will cause the heat to be lost in other ways other than the temperature difference. Okay, so in this case, because it's a trial and error solution, because we don't have the the outlet water temperature, let's start by assuming it's a trial and error. So assuming that the water coming out is 80 degrees Celsius. So using the appendix, you can get the mu of water at 80 degrees Celsius to be 3.56 times 10 to the power of -4 Pascal second. So let's try and solve this. So okay, great job. Okay, you guys got this correct. So let's because I still have some space here, so let's try it here. Okay. So why did we choose 80 degrees Celsius? You might wonder. So because this is simply because we took 1/3. So this is A. 1/3 of the temperature difference, delta T. So between the wall and the water. So the wall temperature or the steam temperature, the outside temperature is 107.8 degrees C. Okay, so the inlet water temperature is 65.6 degrees C. So if you minus this, you will get the delta T. So after you get the delta T, you take only 1/3 of that, so divided by 3 plus 65.6. Okay, so you will get around 80 degrees Celsius. Okay, so it doesn't have to be perfect because we are still doing trial and error. So we'll just take more or less 80 degrees Celsius for ease of calculation. So given this, and considering the previous question, what do you think we need to calculate first? All right. For the student coming in a bit late, it's okay. I will be uploading this video later. And just everyone, please don't forget to sign in to the class. So anyone knows what anyone have an idea what we need to calculate? If you can recall the first question, we usually need to know what type of flow this is. So is that enough of a hint? No one has any idea what you need to calculate first? Because if you don't know this, you would not know which formula to use.
Is it the Reynolds number?
Correct. Yes, good job. So usually we need to know the Reynolds number because we need to determine whether the flow is laminar or turbulent. So great job. So in this case, Reynolds number can be calculated using dV rho divided by mu. Okay, this is still the formula that we used before, and because water is flowing inside the tube, we consider the inside diameter. So in this case, the inside diameter we already have 26.6 meter. This is millimeter. This is correct. So we just change it into meter. So we have 0.026. 0.0266 meter. So the velocity just now is V is not given. V is already given, right? 2. I suppose no one listed that out, but 2.44 meter per second. And then the density will be, the density we can get from the appendix will be 980 kilogram per meter cube divided by mu. The mu is also obtained from the appendix, 4.32 times 10 power of -4 kilogram meter second. Okay, so 4.32 is actually, let's see, 4.32 is actually the viscosity at the entry temperature. Okay, so again, we can just double check that we have all this correct by crossing out meter, 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 and meter cube crosses out, then second and second, then kilogram and kilogram here, everything crosses out. So you can verify that you put in all the parameters with the correct dimensions. You don't need to convert it any further. So in this case, you will get 1.473 5, okay, or 1.473. So 1, 2, 3, 4, 5. 1, 1, 2, 3, 4, 5. Okay, so this is also more than 6,000. So can anyone tell me whether this is laminar or turbulent? Yes, this is turbulent. Okay. Alright, so this is where it becomes slightly different than before. In this case, oh wait, no, this is actually the same. But the formula, because this is also turbulent flow, we are going to use, I believe, the same formula as we did before. So Nusselt number equals to H, the heat transfer coefficient, HLD over K, 0.027 Reynolds number times a power of 8, 0.8 times times the Prandtl number 1/3 times power of 1/3 mu, the bulk mu divided by the wall viscosity power of 0.14. Okay, so again we already have this. We can get this from the appendix, as well, because we have the temperature, so we can get this from the appendix. So we also have the K and the diameter just now. So the diameter again is the inlet the inside diameter. So if you substitute all the information, you can calculate H, the heat transfer coefficient. So D is 0.0266 meter divided by K, 0.633 watt per meter K, equals to 0.027 RE. Oh, okay. So wait. Okay, 0.027 times the Reynolds number, which is 1.473. That this is what we calculated just now, times 10 to the power of 5 power of 0.8, 2.72. This is from the appendix. Power of 1/3, and then the bulk is 4.32 times 10 to the power of times 10 to the power of -4 Pascal second divided by 3.56 times 10 to the power of -4 Pascal second, power of 0.14. Okay, so if you solve this for HL, in this case HL is equals to the inside convective heat transfer coefficient. You can get it as 13,324 watt meter Kelvin. Okay, so how do we so meter and meter becomes meter squared, watt and Kelvin. Okay, I think the first one I missed the Kelvin here. I think you should have here Kelvin here. Okay, so the units check out. Okay, so what did they want just now? They want the HI, so we already here have HI. And then what else do they want? UI. Okay, correct, UI. So this is A, this is B, and I suppose this is C. Okay. So we move on to part B. So part B, they want you to calculate the overall heat transfer, the overall coefficient UI, correct? Okay, let me see. Okay, so for this one, is something that we actually covered a few lectures ago. So let's try and solve this together, because if if you remember, the equation involving the heat transfer, the heat coefficient Ui is equals to this formula. Okay. So or is also the, if you remember, the energy balance, the typical energy balance equation, the heat transfer rate is equals to the driving force divided by the resistance. Okay, so what we want is here. Okay, let's try and calculate the things one by one. So let's start with the area. So area, the inside area is pi diameter, inside diameter times length. So this is pi 0.0266 times the length that is given just now, 0.25. So this is basically the area of a cylinder. Okay, so this is a formula for area cylinder. So you can get 0.0255 meters squared. Okay, so we have this, but let's try to calculate the log mean area, which is pi d inside diameter plus outside diameter times times length divided by 2. So you can just substitute 0.0266 meter plus 0.0334 meter. So these are both from the appendix times the length given in the question, 0.305 divided by 2. So you will get this as 0.0287 meter squared. Okay. So for outside area, so outside area is basically also a perimeter, the area for a cylinder. So which means that the formula is the same as this first one, except that it uses the outside diameter. So pi, the outside diameter is 0.0334 meters times the length. So you will get 0.0320 meters squared. Okay, so we have all the three areas. So in this case, you can find, I'm not sure whether I gave this in the K. Okay, K for steel is also I already wrote it down. So K for steel is 45 watt per meter K. So if you remember the formula for resistance, okay, for resistance will be 1 over HA. This is for the case of convection. Okay. So but for the case for conduction, it will be R0 minus R1 divided by K, the thermal conductivity and area. So this one we have the convection occurring from outside the wall and to the wall, outside the pipe to the wall, and also from the wall. Then after that, it goes to through the wall through via conduction, and then from the wall, the heat from the wall into the water happens via convection. So we have three different resistances to think about here. So the first resistance is the resistance from the wall into the water. So we call it Ri because it happens inside the pipe. So this is we use this formula. So for Hi, we calculated just now. So we already got, we calculated just now 13 1324 watt meter squared K. Okay. Times the area. So the area we also calculated just now, the inside area. So we can cross this. Okay. We can cross this out. Meter squared. Okay. So we will get the inside resistance to be 0.023943 Kelvin over watt. Okay. So for the second, the resistance for conduction, so this formula, so RO minus R1. Okay, so because 0.0334 meters and 0.0266 meters are actually the diameter. So we need to get the radius, because R is radius, right? So we need to divide it by 2. So then after that you divide it by the conductivity of 45. This is for steel pipe. And then for the log mean area, we already calculated just now. Okay. So if you calculate this, you will get 0.002633. And then if we cross out, these are meter, you cross out this meter, with this meter becomes a meter squared, so you can cross it out with this meter squared, so you will get K over W. So this makes sense because this and this are both resistances, so they should have the same dimensions. Okay. So finally we calculate the outside resistance, which is again we use the same formula, and in this case the outside HO, if you remember, has already been given to be 10,500, if I recall correctly. Okay, betul. That's correct. So watt meter squared K. So we calculated the outside area to be just now 0.0320 meter squared. Okay, so again we can cross this out, meter squared and meter squared here, and then you can calculate to get 0.002976, again Kelvin over watt. Okay, so now that we have all the resistances, the sum of the resistances, we have the I apparently pressed something. Okay, since we have the individual all the individual resistances, we can I don't know what I pressed. Okay, so we can calculate the sum of all resistances to be Ri plus Rm plus Ro will be equal to 0.008852 Kelvin per watt. Okay. So if you remember, wait. If you remember we also need to calculate, let me see. We also need to calculate the delta T. Okay, so in this case, delta T, if you remember, this delta T will use the T wall minus T in. So the temperature of the wall is already given, minus the temperature of water going in, so you get 42.2 degrees Celsius. So wait, okay, so in this case, if so just now, because we assume the temperature of water going out, correct, T2. So the thing is, we don't know whether this is correct or not. So now we need to check whether the temperature 2 that we assume, so if you remember, we assume the temperature 2 to be 80 degrees Celsius. So using the temperature difference that we get here between the wall and between the wall and the inlet, the water going in, so we can calculate the temperature drop for the temperature the temperature across the temperature difference across the water. So this difference in temperature occurs within the tube, because it's from the wall to the water. We are concerned about the temperature of the water, and the water is inside the tube. So what we need to consider is the resistance, the inside resistance. So we are not thinking about the outside resistance and the wall resistance, because water is not present in either of these. Okay, so we need to what we do is the temperature drop within the water, or the temperature difference within the water, is due to the resistance, the inside resistance, divided by the total resistance, okay, times the total temperature drop between the wall between the wall and the temperature difference between the wall and the within the wall and water coming in. So like I said before, why do we need to why are we talking about resistances, is because not all the heat is transferred through not all the heat is transferred through convection, then conduction, and then again convection, all into the water. So since there are resistances, the wall has a resistance, and the outside temperature to the wall via convection also has resistance. So that's why we calculated the resistances. So these are all resistances that would cause the heat to be lost. So not all heat is delivered to the water. So, and that's why we need to calculate the sum of resistances. So because this is considering the whole system, because we are considering the wall all the way, this is that's why we consider the temperature of the wall all the way to the water. So this is this will be the sum. This would take into account the sum of all resistances. But if we want to consider only the temperature difference in water, we only need to think about the inside resistance. Okay, because water is only present in the tube. So if we consider only within the tube, so we will get the temperature, or the temperature difference between the water coming in and coming out. So the difference is you can get 14.5 degrees Celsius. Okay, so the difference between the temperature of the water coming in and the temperature of the water going out is 14.5 degrees Celsius. And if you read the question carefully, you will find out that the temperature, you will find out that the water is being heated by the steam. So that means that the outlet temperature of the water is actually higher than the temperature of the water coming in. So if we understand this, we can get the temperature of water coming out. So the temperature of water coming out is the temperature of water coming in plus delta T that we just calculated, 14.5. So this is equals to, what is the inlet temperature just now? 65.6 degrees Celsius plus 14.5 degrees Celsius. So you will get 80.1 degrees Celsius. So since we already assume the temperature of the water coming out is 80, so this is actually close enough. Okay, so if for example you assume it to be 70 and it turns out to be 90, then in that case you will need to recalculate everything. Okay, so but in this case it is it's quite a happy incident that we actually assume a temperature that is very close to the real temperature. So what does the question want just now? UI. So we haven't calculated the overall coefficient. So how do you, if you remember, why is it happening again? Okay, so if you remember the formula just now, Q is equals to UI AI delta T. Okay, and then so we have delta T. We can calculate delta T, and we have the area, but we don't have U, and we don't have the heat transfer rate either. But if you remember, this is also equals to delta T over the driving force divided by the resistance, and we already calculated the resistance just now, and we have we can easily get the, wait, there is a bug in my room. Okay, that's annoying. Okay, sorry about that. So we can get the delta T, and we already calculated the resistances. So if we don't need this, we already have this, okay. So actually this and this can just cross out, okay. So you can just rearrange the equation to be UI over AI times delta R. Okay, so for the AI, we also already calculated it to be 0.0255 meters squared times the sum of total resistance just now, 0.008852 Kelvin over watt. So you can just calculate this and get 4,586 watt per meter squared K. Okay, so this one also settled. So we have the third part. What did the third part want just now? Oh, the heat transfer coefficient. Okay, so that's actually pretty easy because I believe we already have, if we remember, if we use this equation, now that we have U and we have area, of course, and we also have delta T, we can just easily calculate this for the heat transfer rate, which is 4586 watt meter squared K. The area is this one, 0.0255 meter squared. Then times delta T will be the one that we calculated just now, 42.2 Kelvin. So we will get 4,935 watt. Okay, settle. Okay. The thing is, I don't think that we will have enough time because you have a class at 11, right, guys? Or
Yes.
do you not have? Okay. So because I think if we continue, we will definitely exceed 11 o'clock. So since we started early, I will just end it a bit early, 9 minutes early, or by the time I finish talking, maybe 8 minutes early. So we can continue this in the next class, but I will go ahead and share this on e-learning later, and I will also keep the Jamboard here for now, so that you can later go back and you want to test it out for yourself or calculate for yourself and double check with my ugly handwriting, so you can do so as well. So I'll keep it I'll keep the Jamboard in my drive as far as long as possible. So since you are all editors, please do not change whatever that is on this, so that I don't want, so that everyone can refer to this. I don't want you guys to change it and confuse it for your other friends. Okay, so since we do have a bit of time, do you have any questions regarding the second part, the second question, or you need some time to digest and test it out for yourself first, which is completely understandable? Okay, no question? Any questions? I'll stop sharing. Okay, any questions before we end the class?
Doctor,
Yes.
actually, I calculate for the delta t, for the second delta t. So when it show the equals arrow I per r and times 42.2.
Oh, sorry, you're breaking up. I cannot hear you.
Sorry, I think my connection, is it
It's a
clear?
bit, yes.
yeah.
Yeah, I can hear you now.
Okay, so for the second delta t, I got different answer from your calculation. Whereas I got 11.414, but your calculation is actually 14.
Okay, let me share again.
Yeah, I just want to make sure that
Yeah,
is
it's
it
okay.
your calculation?
Is it this one that you're talking about?
Yes.
Okay, so how did you get 11 point something?
Yeah, I just divide 0.0023943 divided by 0.008852, and it's time 42.2, and in my calculator it shows the number is 11.40414.
Oh, you mean this delta t here?
Yeah,
Okay,
the
wait.
second happy.
I thought you were talking about this one. Okay, wait. Let me see. RI, right? 0.02423943 divided by 0.00852 times 42.2. Oh, you're right. Okay, wait. Let me check. Or perhaps I will check and address this question later. If that's okay with you guys. So we'll address it in the Monday class, maybe? Is that okay?
Okay, doctor.
All right, so I will double check this and then let you all know. So I'll let you guys go now, and I'll see you guys next week. Okay, so hopefully we can have a similar class like this, and since I will be sharing it on e-learning, so you can try it out first if you want, but we'll be conducting something similar to this, so you don't need to, if you want to join and during the class and try to understand during the class, that's also fine. Okay, have a nice weekend, everyone. I will let you know when I have uploaded the assignment on e-learning. Okay, have a nice weekend. Thank you for listening, and for the ones who joined and participated, thank you. I appreciate that. Bye.
Thank you, doctor.
Bye.
Thank you, doctor. All right, bye.
Thank you, doctor.